We hear about artificial intelligence every single day, but what's really the engine that makes it all work? Today, we're going to pull back the curtain on neural networks, the powerful, brain-inspired models that are the heart of modern AI. Let's dive in. First things first, let's clear up something you've probably heard 1,000 times. AI, machine learning, deep learning. These terms get thrown around like they're all the same thing, but they're really not. So what's the actual difference? Here's our game plan. We'll start with what AI even is, explore the two historical paths that led us here, and then we'll get right into the digital neuron. We'll break down how networks learn, their specialized forms, and finally, we'll take a peek into the future of AI. Okay, so let's start at the very top and get these definitions sorted out once and for all. At the highest level, we've got artificial intelligence, or AI. This is the big dream, the grand goal of computer science, to create machines that can think, learn, and solve problems just like a human can. This slide explains it all perfectly. Think of AI as the entire universe. Machine learning is a star system within it, a specific approach where we let machines learn from data instead of hard-coding rules. And deep learning? That's a planet in that system, using those powerful neural networks we're talking about today. So just remember, all deep learning is machine learning, but not all machine learning is deep learning. You know, the path to modern AI wasn't a straight line. For decades, the field was defined by a battle between two completely different philosophies on how to create intelligence. This timeline shows that progress came in waves. There were periods of huge enthusiasm followed by AI winters, where funding just dried up because the dominant approaches hit a dead end. And those winters were mostly the result of the limitations of that first path to intelligence. And this slide gets right to the heart of that battle. On one side, you had symbolic AI, or good old-fashioned AI. Think of it as a giant rulebook written by humans. It's a white box because you can read the rules, but it's incredibly fragile. If it encounters something that isn't in its rulebook, it just breaks. On the other side is machine learning, which is the approach that won. It's the total opposite. It's bottom-up. You give it a ton of examples, and it figures out the rules for itself. It's flexible, but it's a black box. We often don't know exactly why it made a certain decision. So the data-driven neural network approach won out. But how do they actually work? It all starts with a single, fundamental, brain-inspired unit, the artificial neuron. The whole idea is inspired by the brain. A biological neuron gets a bunch of signals, adds them all up, and if the total signal is strong enough, it fires, sending a message on to other neurons. It's a simple little on or off decision maker. But when you connect billions of them, you get us. The artificial neuron is just a mathematical version of this idea. It starts by getting data, the inputs. Now, here's the key. Each input is given a weight, which is just a number representing its importance. These weights are the little knobs that the network learns to tune. All those weighted inputs are added up, and finally, an activation function makes the call. Is the signal strong enough to fire and pass on? Yes or no? A single neuron is simple, but how does a whole network of them actually learn to do something useful, like recognize a cat in a photo? It's all about a continuous cycle of improvement. It learns in this elegant four-step loop. First, it makes a prediction. The image comes in and the network says, I think that's a dog. Second, it checks its work. A loss function compares the prediction to the right answer. Nope, that was a cat, and calculates how wrong it was. Third, this is the magic part, backpropagation. The network sends that error message backward through itself, assigning a tiny bit of blame to every single weight that led to the mistake. And finally, it optimizes. It just nudges all those weights in the right direction. Now imagine this happening millions of times. That's learning. Of course, not all problems are the same. A network that's good at analyzing financial data won't necessarily be good at understanding language. So different types of neural network architectures have been designed for different jobs. Let's look at two of the heavy hitters. For anything visual, we use convolutional neural networks, or CNNs. They're masters at finding patterns, building them up from simple edges to complex objects, which makes them perfect for computer vision. But for things where the order of the data matters, like words in a sentence or stock prices over time, we use recurrent neural networks, or RNNs. They have a form of memory, letting them use past information to understand the present. These networks have already achieved incredible things, from creating art to diagnosing diseases. But the story isn't over. Let's wrap up by looking at the biggest challenges the field is facing and what's next. Despite the hype, there are significant hurdles. First, these systems are incredibly hungry. They need massive amounts of data and colossal computing power to train, which can be a serious bottleneck. Then there's that black box problem we mentioned. Not being able to clearly interpret why a decision was made is a huge problem, especially in high-stakes fields like medicine, where knowing why is just as important as knowing what. Which brings us to this final, crucial question. Today's AI is phenomenal at pattern recognition, but it doesn't truly understand or reason the way a human does. The next great frontier might be to combine the data-driven learning of neural nets with the logical, rule-based reasoning of good old-fashioned AI. Can we build a system that not only learns from the world, but can also explain its thinking? That's the challenge that will define the next chapter in the history of artificial intelligence.